So how was the week in general, last week? Any feedbacks? You want to comment, make a big comment or something? Thumbs up, thumbs down? Oh, Tatiana, thumbs down.
No, one is up, one is down. Our
okay.
machine in Fablab Zagreb was broke down and we couldn't finish task. So it was funny.
Okay.
We did the half of the job, so we hope they will fix it so soon and we will be able to finish our tasks.
Okay, good, let's hope so.
Yeah, me too. And Ivan is also.
Okay, so what we have this week? 3D printing and 3D scanning. Woo, amazing. Okay, let's go to the class. Today's class is going to be the lecture, more or less a 1 hour lecture. Okay, now the mic. And then we will divide again into 3 stations. One is going to be FDM, 3D printing. Another one is going to be 3D scanning. That is going to be in the Fab Academy room. Another one will be UV curing resin, Sla Lcd type, on the old office. And I hope works because today both computers of the Fab Academy room, they don't want to switch on. Let's hope they can fix them, because if not, we can do the 3D scanning. So let's go on to 3D printing. So just a little bit on the 3D printing history. 3D printing is a technique that most of you have heard just in the recent years. Who has ever 3D printed? Raise the hand. Okay, yes, half of the auditorium more or less. So some people is not sure if he has used it, maybe on the dreams. So the 3D printing exists since long time ago. Another completely different thing is that has become like popular, or you can find in like a lot of fabrication spaces. The first patent of the first trials of 3D printing were invented by Chuck Hall in 1983. But since then, like 3D printing was in this like what we consider still mode, was only for research and big industry development. So it was patented and was not widely used for the outside markets or the common everyday user. That changed a lot with the RepRap project. Has anybody here about RepRap? Okay, 1, 2, 3, 4. Whoa, that's a lot. So the RepRap project is an open source low-code 3D printers or family of printers that were born with the idea of self-replication. What does that mean? That the machines were designed to have the less amount of what we call vitamins. What we consider a vitamin? A vitamin is, for example, a bearing, a rod, or external parts that you can buy. Most of the parts of that make the printer were initially designed to be made out of 3D printing. So when you build the first 3D printer, that, as far as I remember, is called, like in the forums, is called like Yoda or something like that. They call it with Star Wars names. You could actually print parts with that 3D printer to build another printer. So it's about self-replicating of machines that build machines. Just a little bit on the history before that and before that happened. Like the technologies on 3D printing were evolved since the 80s, more or less in this order. First, the machines that were designed were not what we considered FDM printing. That is what most of you have heard about, was the SLA and Loom and SLS patents. And all of them were mostly comprised by 3D Systems and Stratasys, like the 2 biggest companies of 3D printing in the world. They keep the patents closed until more or less 2005, 2003, I don't remember right now, that the patent went out of date. And then opened up the technology to other people to be able to use it. In that part, the 3D printers were huge, big, bulky, and really, really expensive because they were only designed for industry and heavy industry use, and not, sorry? And not something that you could have at 3D printers that we have right now. They are not exactly a microwave that is in every house, but it's close by. Like we are right now in the stages of how 3D printers, as people should have the first computers at home. Not everybody had 15, 20 years ago, not everybody has a personal computer at home, but it's something that you start seeing in some fields, especially right now, we have it for designers. Like right now, I almost don't know any designer that does not have a small 3D printer or a cheap 3D printer at home to allow it to prototype and test a few models. What happened in 2005? As the patents went out of date, the first 3D printers replicated or not replicated, not everything was RepRap, started. And in 2009, Makerbot initiated as a company. Makerbot was a small company based on New York that started selling DIY kits made out of, anybody guess what the material were made these machines? Come on, you have a picture. Laser cutter, actually it was laser cutted frame, wood frame, plywood frame, and a lot of small parts that you made you assemble this small 3D printer. The small 3D printer was called actually Cupcake, because the maximum size that you can print is more or less the size of a cupcake. And the quality was not really good for the time, but for the times was amazing. If you are interested, I think we have still one of the original cupcakes, first 3D printers made out of laser cutter. After in the Code Club, maybe Oscar can show you. It has exactly the first assembled 3D printer that came out probably from Barcelona, directly from New York. So that started with a Makerbot, that was a company that was later one of the biggest companies in 3D printing, if we don't talk about the big three, that is Stratasys, 3D System, and sorry, I forgot the name right now, but let's say there were three big companies that more or less will earn like millions and millions and thousands of millions of dollars yearly. Was the first small company that started making 3D printers in the market. And they made it open source. That later evolved the company and become like more or less what we call a medium-sized company, and was then acquired by Stratasys again, closing again and closing the open source files of their printers. 3D printing is a additive manufacturing technique. What will be the main difference among other different manufacturing techniques? The most widely used, and one of the techniques that you used last week and 2 weeks ago, was you use the PCB to produce PCB files, like in the mini milling machine to produce PCB. That is a subtractive technique. You start with a layer of material, in this case copper, and you take the material out. With laser cutter or computer-controlled laser cutter, what you do is you start with a blank of material, it's in a sheet form, and you start burning material away. In this case, we start with a bed or a surface that is completely empty, and we start adding material on top. What are the main differences? One, the subtractive, of course, wastes material because you are destroying or even like producing small chips of the material that can later recycle or not, depends on the material that you're using. Generally, it's more expensive, as the equipment that you need to have to produce the files is heavier, stronger, and in a more industrial grade, because the tolerance that you produce with machining needs to be higher. The surface quality is better in general. It's more precise and has better tolerances, and is suited for mass production. One we mean is suited for mass production is one of the first machines you will find out in any manufacturing industry is a CNC machine. It's one of the first ones and easiest to find. It's actually one of the most standard ones all around the world. You can go from like Netherlands to Afghanistan, you probably will find a wood shop that has a CNC machine. And it's the basic equipment all over the world. And one of the most standard ones. Additive, on the other hand, reduces the waste to zero or virtually zero. Depends on how you make your file. You will need to use supports or not. That is a part of waste material. But in general, we consider it as zero or minimal waste. The material is cheaper. That is not exactly true, because you have a lot of types of materials, depends on the one you want to manufacture. You can manufacture in PLA plastic, that is polylactic acid, that is a really cheap plastic, or you can manufacture in additive titanium. Of course, the difference between PLA and titanium is huge. Has usually a clear and easy user-friendly interface, as making the files for 3D printing in general is as difficult as designing the file. The most difficult part is designing the file, not actually on producing what we consider the CAM part of the file. In 3D printing, CAD is the difficult, CAM is the easy, in general. The surface finish is worse than in subtractive manufacturing. It means we don't have that high tolerance and precise tolerances, and the surface finish will depend on the technique you use. For example, FDM printing produces poor surface finish. SLA printer cannot produce smooth, shiny surfaces. Loom can produce them, but still you have like layer on the side. One of the worst constraints of additive manufacturing is the non-homogeneity on the strength of the parts. Why? We are adding material. Imagine that you are building a cathedral or a wall. On one direction, on X and Y, the bricks are really strong. But if you try to splice on the Z, you can take if the bricks are not glued with cement, you can move the bricks up. Will be the same more or less in additive manufacturing. The pieces are way weaker in the Z axis than in the X and Y. I would say that is not completely true. Like, there is not always a golden rule. Depends on the machine you use. At least you always have one axis that is weaker than the other ones. Some machines they have in Z, some machines they have in X, some machines they have in Y. Depends on the machine you use. It's good because it's easy to automatize and it's easy to make production farms. It means having a lot of 3D printer producing a lot of small parts at the same time, and without having almost no supervision. There are three big families on 3D printing. One is considered FDM 3D printing, that is fused deposition modeling or filament deposition modeling. Basically, we use a thermoplastic set that we heat up until the liquefied point of the material, and we push it through a small nozzle, a small pipe, to reduce the amount of material that we can deposit to an average size of 0.4 millimeters on the nozzle point, and we start drawing with melted plastic. Imagine that you are making 3D print with, for example, your toothpaste. It will be the same, but on a really, really small scale. And instead of having to squeeze, we just heat up to push the material through. We have Sla Lcd Dlp Technologies that we can consider like liquid printing, where we have like a UV reactive resin that hardens onto UV light. UV light frequency is more or less comprised between 300 nanometers and 495 nanometers of frequency wavelength. That means with a different light source, could be a laser, a UV LED, or a DLP projector, like similar to the one that we are using right now on the main screen, that produces a high source of UV light. We harden the resin. What we do it doing layer by layer, and in general, this technology has way higher accuracy, but the strength of the parts is really weaker than in other techniques. And then we have the power bed. In here we consider power bed, and we can include SLS, MPG, MFG, like there are a lot of terminologies for this kind of technology. It's a technique that we start similar to a subtractive technique. We start with a big block of material, and we harden the material that is inside. It's in powder state, and we harden only a few parts of that powder state. Depends on the technology. We can start with a big base of material, or the base can get filled at the same time that we are printing. In this case, it will be like a similar process to take the part out as when you find a coin in the beach. You need to find the coin, the hard part of your part, inside the other 3D printed material that hasn't been harder. This technique produces really high quality surface finish, is one of the best ones. The average of the strength of the parts is also good. What's the con of this technology? Is the price of the material is really harder, way higher, and the parts are more difficult to manufacture, and the equipment is way more expensive. Just to have you an idea, from left to right, fusion is 1 kilo, 20 euros, SLA is 1 kilo, more or less 100 euros, that number is changing. Right one is 1 kilo, 1,000 euros as a minimum. So basically we multiply by 10 the price of the raw material, and on the manufacturing equipment is almost close to that also. Like a cheap 3D printer for FDM, right now it's around like the 2,000 euros target, let's say, like not like a good quality equipment, is 1,000, 2,000 euros target. SLA is around like 5 to 10,000. Power bed is easily like 20, 100,000 or even 1 million, depends on the technology. Printing principles. Even if we have, yes? How do we harden the powder in the powder bed? Depends a lot on the technology. I think that for the left one, FDM, we have more or less 3 types. FDM, FFF, or like there are 3 acronyms for this kind of technology, and they are more or less do the same in different ways. Will be like pellet place extrusion, etc. SLA is the same concept, but will be a laser projector, UV light source, or other ones that use also oxygen to oxidize the resin. In case of the powder bed, changes a lot. And actually, these where like each manufacturing company and 3D printer manufacturing has its own terminology and technique and approach. We can comprise them in different ones. One will be like multi-jet fusion printing. Multi-jet fusion printing, yeah, sorry, like the terminology sometimes is complex. Is you have with a powder bed, and basically it's a similar system as a normal 2D paper printer. You have inkjet cartridges launching micro dots of a special ink. It's not ink, in this case, it's a additive blank binder. It's a binder that binds the powder together on a really small scale. We have other one that is like energy light deposition, ELD, that is basically a high power laser or laser sintering of the powder. In this case, this technology is mainly used for like powder-based metals. For example, aluminum, titanium, and steel are binded using high power laser that focus on the powder particles and melt them together at a microscale. Then those pieces need to be post-processed with another machine and put in an oven, but in short term it's like that. And then we have loom. It's a similar process, but works by pressure and heat on the bed. Like, it's complex to define, like, use a few technologies, but in general it's multi-jet fusion, that is by throwing a binder with cartridges, or a laser and a cartridge, or pressure and heat. But basically, the powder is hardened through a process. In general, it's laser or jet, like multi-binder jet. They are the big 2 branches. Then inside you have like, I don't know, 50 types. I don't know all the processes too. Like, they change a lot every year. So, what do we have? Printing principles. We always start, and most of the 3D printing machines, I will not say all of them, but most of them start with an X, Y, and Z axis. The X and Y are the slices that we want to print. Basically, imagine that you will have any printed object, and you just cut it into really small layers. like a carrot cake. A carrot cake, you had see the layers, just imagine this in really, really small. You remember in laser cutter that we can produce 3D files, but cutting the slices and stacking the material on top will be a similar process. But the difference is we don't make them, the slices individually, we just make one on top of each other. And then we have the Z-axis that when we finish one of the layers, we move one up, one layer up, and we keep printing the next one. It's a similar, always make the comparison of building a cathedral church. Like you start putting bricks, and then you move to the next one. And sometimes you need scaffolds to keep your pieces to not fall down. Let's see what's that later. All the machines have a bed. Could be a powder bed, could be a liquid bed, or could be an empty bed that just heat up. That is the build platform. We have the extrusion head. Could be a hot end, like in FDM. Could be a laser beam in SLA. Could be a multi-ink inkjet binder. And we have the intake of the material. In the case that you will mostly use is FDM, is the filament. There's the material that comes in filament winded. And support filament, you have a multi-axis machine, multi-material machine. This is one of the most important facts on 3D printing and additive manufacturing, is resolution versus time. As the definition of the model is not determined by the X and Y axis, it's determined by the size of the slicing, this clearly informs the speed and quality of our build. We can slice at bigger layer height or smaller layer height. A smaller layer height will produce really small layers, but we will need to produce a lot of them. Meanwhile, a big layer height will produce less amount of layers, but each one of them will be thicker. And there is a clear definition on the time the machine takes versus the quality. More or smaller layer heights means we need to produce more movements. We are depositing less material every time. That means also the layer heights are less prone to be seen, and by so the surface quality increases. But with the surface quality increase also came out increase on the time. Why? Any clue? In a theoretical world, theoretical context, both could take the same time. But we have something that is called physics. Like the machines have a speed limit. And if your speed limit is 100 and you need to move 3 times, it's going to take 3 hours, for example. But if you need to move 100 times, at 100, it's going to take 100 hours. So the more movements you need to produce, the longer it will take. You are depositing less amount of material for the same amount of time. So it will take more time. The time curve is not linear, it's exponential. So if you start with this more or less is 0.1 and this is 0.3. If this is a time frame, let me draw in another color. I don't know, 0, x time, sorry, x time, and this is 0.1 and this is 0.3. If we start more or less here, when you start increasing the quality, the time exponentially drops up because the machine has still the same speed limit. And we can play a little bit with this value. This is not exactly a straight line, it grows exponentially. But that's also, this depends on the technique they use. Some machines they cannot have really big layer heights. Why? You asked before, how do we harden, for example, powder bed additive manufacturing techniques with ink? The amount of deposition of the ink needs to be really, really small. So actually we cannot produce really big layer heights. What makes these machines really expensive is, as they cannot produce big layer heights, but they need to compensate by having a really high printing speed. So basically, when you print with a powder bed, the machine like makes like this, print all the whole layer really fast. It will be like a 3D, like a scanner. It's moving left and right really fast to compensate the amount of Z speed, because we are doing a really high definition. For example, with FDM, we have also a constraint. With the constraint is the amount of plastic we can melt per second. You cannot do 1 millimeter layer height with a normal FDM printer. Why? Because it's like having a hot glue gun. Even if you press harder, the glue at some point doesn't come faster. The pipe or the nozzle has a certain diameter, and the heat power dissipation of the nozzle point is like, I don't know, X amount of watts. X amount of watts can only melt, for example, 100 grams of plastic per hour. And actually, that's one of the definitions, for example, with FDM printing. What is the heat consumption power or the heat transmission power? You have some printers that can output more grams of material per hour than other ones. For example, maybe you have seen here like a few 3D printer samples. In big scale 3D printing, we consider, okay, I don't want to know what is the printing speed of the machine. What I want to know is the amount of kilograms per hour of the machine. Because if you know the amount of plastic that you can melt per hour, you know more or less the volumetric output that you will have in total. We will go in deep in this later. But as we say the same for the Z, we have also a resolution on the X and Y. The resolution on the X and Y is the curvature and how the stepping is interpolated. Imagine that you are moving in a Cartesian mode. That means we are moving in X and Y. And doing a diagonal or a curve is a mixed movement between X movements and Y movements. Imagine that you are moving in a grid and your minimum, this is a grid, this is the minimum resolution that you can move, like a chess. You can only make movements like this, because this is your minimum step size. And this is about machine tolerances. That means what is the resolution? And the minimum step size will define actually how smooth your curve will be, because your curve is not defined by a curve, it's defined by micro movements in Cartesian mode. In general, this value, and now is clearly overkill by the technology. In the later years, the resolution of even one of the worst machines is around like 0.05 millimeters. That is clearly way enough for most of the applications. But it's something that, for example, in precision milling machines, in the case that you have right now, last week, it was produced in a PCB, is really important because you are cutting with really small objects and you really need to produce really high and accurate finishes. Why the resolution is important? For example, in 3D printing, it's important because Sla Lcd Dlp techniques are widely used, for example, for doing teeth implants. It means mouth implants of your teeth, of reconstruction of your face. In this case, the tolerances are really important. And that's why, for example, SLA techniques usually have a high curvature and high definition on the X and Y, and that's why one of the reasons why this technology is used. Definition of how a 3D printed part comes out. When we 3D print something, this depends a lot on the 3D printing technique that you use, but you can produce not
Još ja rekao, de moram doći malo do vas, rekao, nikako sve trčim lijevo, desno. Rekao, i Darin mi je bolestan, rekao, aj kad on malo ozdravi da mogu ga, rekao, negdje ostaviti i to.
Okay, this bottle is a 3D object, no? But it's empty inside. In 3D printing, we can also customize if this object is completely hollow inside,
I
or has
pitam,
some
reko,
material.
kako je
Or we can produce
Željo
it at
stoji
a solid
krajnje
block of
priča s
material.
Bosnićem.
Depends on the technique, you can do it or not.
I kao,
For example,
malo je
in
bolje
SLS,
ovo, ono,
SLS type,
mislim kao bolje je,
the
ali jer
overhead
ono.
usually produce solid objects. And why
I
this is
čovječe,
important?
jutros
What is
mi
one of
Andreja
the main cost of
kaže,
3D printing?
kaže, si vidjela na
The material.
Fejsu.
So if you can spend less material
Rekao, šta je sam
and
vidjela
still
na
produce the
Fejsu?
same strength object,
Kaže, umro
you can save
Željo.
a lot of
Evo
money
te kad se nisam
and also time,
onestjeskla.
as you don't need to harden the material.
Probala sam
What
ju
takes time in 3D
nazvat,
printing is the amount of material that you harden
probala sam ju
per second.
nazvati, ne
If you
javlja
harden less
se.
material, it takes less time.
Mislim,
and
okej,
also less
logički
money.
mi je da se ne
So actually we
javlja.
are able to customize and produce
Poslala
and
sam joj
control the amount
poruku
of material that is
da ako
deposited
šta
inside
god
the 3D printed
zatreba da mi
object.
se javi.
As we can control what is inside, we also can control what is the thickness of the shell of the
Bože,
contact zone with the
strašno.
exterior. So we can control the amount of layers that we have around.
Jebi ga.
Like how thick is
A
the
taman
wall
su
that
renovirali kuhinju,
touches
dečki se
the
sredili
exterior
posao,
of the
cure,
solid
žene,
object.
ovo ono.
This is called shell thickness.
Ovo ja mislim
and
da
is
se i
divided by
planirao
between
ženit uskoro.
top, bottom thickness and side walls thickness. And what happens if you have a 45-degree angle
Sad su
and it's not straight? Actually, in most of the considerations, this is always considered a
Sad su, kažem ti, renovirali malo stan,
Sidewall
napokon ima
thickness.
kuhinju kako je htjela.
And it's important because
I
with
ovo
this
i
you can
ono.
produce really weak or strong parts.
A ošla je u prijevremenu
As we can
mirovinu
play
da
with
može
the
s
exterior,
njim biti, da
we
mogu
can
njih
also
dvoje
play with the
šetat,
interior. The interior is called
da mogu
infill
uživat
percentage.
malo.
And we can choose on using between 0 to 100% infill. It's really important because clearly informs the total strength
Pa ti
of our
čekaj,
material
Janje, ti
and the
čekaj.
total time that we spend on printing. The most widely used infill percentage are between 15-10% to 30%. Unless you want to produce a really strong
Šta?
part, you don't want to print
Ne
higher than
čujem te, ovi
30%.
ovdje mi pričaju.
Actually, printing higher, and there's a lot of studies that printing higher than 50% doesn't actually strengthen our parts, it just make it weight more and spend more time
Dobro.
on the print. And you will say, why?
Ajde.
Because think, for example,
Ciao.
how honey, like beehives are made. Beehives are really strong structures being in nature, and like, for example, also like, how you call it, plants, the lignite inside the wood is not fulfilled. It has honeycombs and structures that are way stronger, and they don't need to fill with material to get the same strength. So we can produce these kind of designs and artifacts inside the 3D printers and still get the same strength as we have fulfilled the material inside. Usually we don't get higher than 50% because it doesn't actually strengthen our parts. And then you will say, why in that case we want to go higher than 50%? You may want to go higher to 100% when you want to make fully waterproof parts. In most of the 3D prints, we are making lines after another line. If you look at a microscope, some of the lines might have some bumps and might let a little bit of water under pressure, for example, or a liquid under pressure, go through the material, cross the box. If we have a reticular structure, the liquid will go inside and slowly go to the other side. So in case of fully waterproof structures, we want to make them fully filled. So we create a thick wall that avoids the liquid to go through the part. For example, let's say you are designing a 3D printed water pipe. I don't know, for example. In that case, you want to print it fully infilled. At the same time, yes? Automatically. No, the interior shape, you don't need to design it. The CAM parts for additive manufacturing automatically generates them for you. And you can choose between different options. We have rectilinear, quadrangular, triangular, there is gyroid, there is one that even like makes, this one is funny, but makes little cats inside, drawing, like it's a really big infill. I don't know why it's really useful, but produce cat ones. So you can produce parts that are really light, parts that are really strong, and you can mix both shell thickness and infill to produce really strong parts, but easy to puncture parts. So you can play with both parameters individually. There are different types of infill patterns. The most widely used are rectangular, is one of the standard ones and one of the first ones to be created. Then we have triangular. This one is stronger, but what happened? We are printing more material, so in fact, it takes more time to be printed. We have honeycomb. It's a really good balance between strength and material safe. And then we have wiggle. Why we will use wiggle? As as we don't have a really strong definition between the different layers, what we can do is to create a semi-flexible 3D printed object in just one direction. It means non-uniform strength print. If you press in this direction, for example, the print will be really strong, as we have a wall connecting both sides. But if we print in this direction, there is no supports between both layers. So the material can get compressed in this direction, and we can make parts that are not equally deformable on both directions. This one is a little bit more difficult to play and is clearly informed by the materiality that you are printing. Gravity limitations. We are printing, stacking material and layer after layer. What happens, for example, when you are building something, a building or a Gothic church? You use scaffolds. So actually the dome that you have on top of your 3D print doesn't fall. So we need to use supports. And we have what is called the overhang angle. That is the maximum angle that you can print without supports. This is defined by two different things. First, the material that you are printing. Some materials can produce higher overhangs than other ones. Some materials can go over 30 degrees, and some materials can go only on 60 degrees angles. Also, the layer height. As we have seen in this previous slide, higher layer heights, it means our cuts are bigger, but also we are moving at the same time more on the X and Y. Imagine that I'm cutting this and then this. I have more space between these 2 points that, as I was cutting really small layer heights, the distance here is smaller than here. So actually higher layer heights reduces the amount of overhang support angle. Smaller layer heights, you can increase the overhang angle and produce prints without a little bit less of supports. When we go over the overhang angle threshold, we need to establish and produce some supports. And these supports you could, and to answer like the infill is automatically generated question, supports could be manually generated or automatically generated. There are programs to actually optimize the generation support. Why? Generation support is material that you print. First is waste. You don't want this under your print, so you will take it out later. Second is material that you're printing. So printing support increases the total print time. And it's important, for example, in your case, you will not matter too much if you print with supports or not supports, because you're working materials that are more or less 1 kilo, 20 euros. But when the material is 3,000 euros per kilo, having 1 gram of supports is a big amount of budget that goes on to print something that you will trash out. So reducing the supports is quite important. So here is what enters the piece orientation. If you are printing, this is a This is a polyhedral that has more or less the same size. If you are printing on the side, this shape, you need support. But if you just flip 90 degrees, 90 degrees this piece, your piece will sit flat completely on the surface, and the angle, you don't have any supported area, so you will print without support. So rotating the part and how you rotate your part to orient your model is really, really important. For example, some manufacturers, yes? Sorry, I don't see. Can you get closer, please? Okay, changing the resolution of the layer height meanwhile we print. Yes, it's possible, and actually before, a few years ago, was not possible, only in industrial ways. Now it's way easier to do it. It's called adaptive layer height. And yes, it could be possible, and depends on the CAM software that you use. The slicer, what we commonly know as represented as a slicer, will allow you or not allow you to do it. So in case you have, like, for example, some areas that you don't need resolution, but you need to print fast, you can increase the layer height. And other ones that you have like a small detail, I don't know, you have a little engraving on the sides or like letters that are really small, you want to increase the layer height. That is called adaptive layer height, and yes, right now it's quite easy to do it. Some 3D printing techniques can only be used with support. And that's a little bit annoying, but for example, in SLA printers, it's almost mandatory to print your object in support, because it's how the material gets attached to the bed or the surface of the machine. It doesn't allow you to print your object directly on the bed, because if you will print it, you will not be able to take it out without damaging your part. So in order to save the quality of your part in like really high-end quality printers, you always print one support. As I said before, most of the CAM softwares allows you to automatically generate supports, but you can use specific softwares to generate supports. For example, this is the same part printed with a standard like support generation and optimized support generation. In this case, we are printing like what we know as branching, small trees, that we have a small contact zone that then open up to create ramifications to have more contact zones and support the prints in the parts we need. This is usually done with optimization algorithms or generative algorithms. Importance of the orientation. Sorry, I need to check the time. 1 second. Okay. As the prints are weaker on the Z-axis, it's really important how you arrange your part when you want to produce a structural part. For example, this is a little nut called chat, because we want to put a screw here inside. Okay, we put the screw. The screw is going to pull in this direction. If we put the screw in this one, this object has been printed using the Z slices in this direction, and this one in this direction. Which one will be stronger? This is a question. Both opinions. Actually, this one. Why? Because we have continuity on the material from here to here, side to side. And then we put another layer side to side. So that means the forces that we produce here are evenly distributed through all the print. Meanwhile, in here, we are attaching the legs of the screw on each one of the layers. So where the screw finish, the forces translation through the parts are worse. So basically, we don't have forces translation through all the parts. They don't jump really well between layers. So if we pull this screw, probably the piece will break in half. Meanwhile, if we pull this screw, this will hold quite well because we have homogeneity. If we just cut this, we open in half, the material is homogeneous completely on the X and Y. It's one unique piece of material, but really, really thin. Meanwhile, the other ones are just material stacked to each other. And this depends a lot on the material you print. And this call is layer bonding. Some materials have higher layer bonding than other ones. For example, PETG is a material that is these plastic boxes or like water bottles are made of, is a really, really, really adhesive material. The layer bonding of PETG is way higher than the PLA. So depends on the piece that you want to produce, you might want to use one material or another one. But that's not the only thing that is informed by the layer orientation. It's also the quality. This is a cylindrical object. It's a perfect cylinder. If we print in this direction, the quality is perfect. But if we print in this direction, you can see just how this shape comes out. This is a cylinder. We are cutting the cylinder layer after layer. And what happens when we build layer after layer? We have overhangs. Even if this is a cylinder, we are cutting layer, layer, so basically we are creating small stairs. So the definition on the quality
ali ne mora, mislim, nebitno. Znači nešto tako u krug se okreće, imamo torić dole da se okreće u krug i da napravim tu neku jednostavnu kontrolu koja će to okretati u krug. Kužiš, imam već onda dvije komponente su nužne, minimum. Znači da imam rezanje u šperploči, imam motor, odnosno programiranje, kužiš, i to su dvije, sve ostalo je bonus.
This effect in FDM type of printing is enhanced like incredibly much.
Sad bi baš bilo fora osmisliti
nešto. Let's go a little bit of the different types of manufacturing. FDM or FFF.
Kužiš.
Basically start with a piece of material that is a thermoplastic. There are lots, I don't know, I can't even count the amount of thermoplastic that exists. It's a material that when you heat up, it becomes semi-fluid state and you can push it through a small pipe, in a general term. There are not other different types of thermoplastics that, for example, I think, yes,
i dalo bi se nešto možda, znači to nešto što bi bio mobil, kužiš nosače, izgledati ili isto karit, i 3D printer.
Thermoplastic sets are plastic that melts over temperature and plastics
htjela bi njemu to napraviti,
plastic that doesn't melt over temperature. They melt through a chemical reaction. For example, epoxy is a plastic that doesn't melt, gets burned on heat. But for example, ABS is a thermoplastic. So not all plastics are thermosets. That's really important to understand. This kind of technique uses filament of plastic, that is a line of plastic. This line has two standards, 1.75 millimeters and 2.85 millimeters filament thick, to actually transport the material to the hot end. It means the hot nozzle when you melt the plastic. There are another different type that is called pellet plastic extrusion. Instead of having the plastic in a filament shape, you have like small grains of plastic that is processed for industrial, and they are more or less the size of a rice grain, and you melt them by pressure and by pressing them. What are the advantages of using these both technologies? First is one of the most affordable techniques on 3D printing. And is a technique that is quite reliable, fast compared to other printing techniques. What are the disadvantages? Like the surface quality of the prints of these techniques is low. When we mean low, it means resolutions of 0.1 millimeter. In manufacturing, 0.1 millimeter is a quite low resolution. A high resolution is 0.001 millimeter, something that you cannot even see. The speed is relatively slow. That depends a lot on the printer that you use. Consider with other 3D printers, like more industrial grade, like powder printers, I will say that it's faster. Shaping interior surfaces is easy. And right now, this has improved a lot because we have increased a lot the total amount of material library that is being able to produce with FDM printer. It's one of the technologies that has made 3D printing so popular. These are some clear examples of standard shapes that you can produce, and you will see if this technique has been used to produce this kind of object because it's clearly easy to see the lane height of the prints. When we FDM print something, first you need to think, okay, I want to design the piece in order to be printable. Something that is a really misconception or something that is bad, not only for 3D printing, but in general for manufacturing, is you design for manufacturing. You are here to learn how to print, how to mill, how to laser cut. If you know already the technique that you will use to produce your parts, you can design accordingly for that. So for example, right now you know that your laser cutter has a curve. It means you have a tolerance. You can design your parts according automatically to that tolerance. You know that you're going to use a 3mm material. You can design thinking that you will use a 3mm material. That is one of the first steps of design for manufacturing. You don't design something and then you don't care how it's being produced, or you think on how you will produce it after designing. You always design thinking on how you will manufacture. Then you produce a 3D model. It's the CAD part, you can use whatever softwares, like so far, I don't know any software that cannot export to a standard STL format. Then you slice. It will be like the CAM part. Is the what we call a slicer. Send your model to the slicer. It what will make the cutouts, will automatically generate the infill, the supports in case you need, set you the total amount of walls and shell thickness, and then you will print it. That is produce the G-code file. Some printers that don't use G-code, they use all kind of scripts, but in general it's like G-code to print it. These machines, they work in this diagrammatic concept. They work by pushing material in solid state with some gears and motors, and then melt the material into a hot nozzle. The hot nozzle of most of the 3D printers is 0.4 millimeters. But here you will have the ability to see like 0.4, 0.6, and 1 nozzle diameter. So you can change the total amount of plastic that you melt per second, have lower or faster printing times, and also see the difference in the resolution. Higher nozzle, if you print with more material, so the resolution is lower, but the print time is way faster. There's always a relation between quality versus speed. Then you have the print bed, the heat bed, that in most of the cases is a heat bed. It's a bed that is hot to help the material get stuck into it. You have two different types of FDM printers. Normal extruder is what we call direct drive, and remote extruder. Why we have this difference? We have some gears and motors close to the nozzle. This technique, in general, is more efficient and can print with more and more technical materials. For example, flexible material. Imagine that you are pushing a rope. If you push a rope, the rope gets compressed. So if you push something that is flexible, we need to push it really close where we want to pull it. Meanwhile, if we have flexible material, if you push here, the rope the flexible will start like compressing and not getting pressed well enough. This is called Bowden Extruder. And you will say, why in that case we have Bowden extruders? It will be the same as you are running in the street with a backpack. A backpack that is light, like this, that the motor is on the back of the machine, can go faster. If you have a camping backpack full of things, this becomes really heavy, and that means this printer is slower. So it's a deal between maximum printing speed of the machine and amount of materials that you can print. Direct drive extruders are prone to be used for technical materials or flexible materials and you can print more materials, but they are slower than, for example, remote extruders. That these machines in general, they are faster, in general they produce good qualities, and they are also slightly cheaper to be produced, but on the other hand, they cannot print, for example, flexible materials or really high technical materials that are difficult to print. Plastic comes out in filament and pellets. Pellets usually mean for like large 3D printing scale production. The two big families of thermoplastics, ABS and PLA. PLA is one of the most widely 3D printed FDM plastics all over the world. It's cheap, it's affordable, and has a negative carbon footprint. That's quite important. Why? Because it's a bio-based plastic. It's made out of sugarcane, corn, or other materials. Like,
s obzirom da mi imamo filamenta u svim bojama, jel tako?
Sorry, I don't hear you. 1 second.
Da.
Someone here was pointing out that PLA actually this is something that is not only for PLA, but in general in the industry right now we are having like this grease washing of all the products. PLA is usually sold as compostable. As stated there, like it's only industrially compostable. It means it only can compost over like a permanent state of, I think it's 6 hours over 90 degrees and a certain controlled atmosphere to actually compost it. But then this not only happens with PLA, it happens with almost or everyday life products that they say, this is compostable, this is biodegradable. That's a lie. You cannot throw it to the nature and it will degrade. PLA actually right now has been widely used, and you can see some studies like what happens if you throw PLA over 10 years in the nature. Basically just
mogu iskombinirati taj mobil sa onim senzorom što smo već kao stavili.
Most eco-friendly plastics that we have right now, thermoplastic sets. And
kao projekat što imam, onaj što prati disanje, temperaturu i to.
To produce this plastic actually sequestrates CO2 of the atmosphere more than actually is being used to produce the plastic later on that crop. Meanwhile, for example, ABS is a petroleum-based thermoplastic. That means it's polluting, but at the same time, it's one of the most widely used plastics that we have right now. Most of the
ne znam šta.
Jer
ovaj kup kolektor je dobra ideja, ali me strah ventilatora. A ne znam kako oni reagiraju ako mi projekat ne radi. Svačaš?
The things that you will care most is ABS in general is way more difficult to print than PLA. PLA is like the most friendly plastic that you can print with. ABS, on the other hand, has some particularities, but also can produce stronger parts. The main difference will be the melting temperature. For example, melting PLA requires between 190 to 210 degrees. Meanwhile, ABS requires 230 to 250 degrees. Most of the cheap economic 3D printers have a temperature limit of 250 degrees. So not all the 3D printers can print ABS. And you have another temperature. What is the second temperature? This is bed. 0 to 60, 90 to 110. It's the temperature that the plastic starts liquefying. You have two temperatures. One, that the plastic becomes completely liquid, and one that the plastic starts liquefying. It means PLA at 60 degrees starts becoming malleable. It means you can compress a little bit. It's like a little bit of Play-Doh. Not exactly Play-Doh, but kind of Play-Doh texture. That is the temperature that you want always on the print bed to be set up to help the bonding of the model on top of the bed so it doesn't move. Meanwhile, ABS, the temperature is way higher, 90 to 110 degrees. And you will say, why this is important? Okay, just imagine, your first 3D printer. Wow, amazing. You print a phone holder for your car. Perfect, it works perfect. You put the phone holder in the car, and it's summer, it's Spain. The car is in the sun. The interior of the car, parked in the sun in Spain, will easily go to the 60 degrees. So that means your plastic phone will start like slowly melting and bending with the heat that you have inside the car. So that means your part is not structural and cannot afford the working temperature range that your phone holder was designed for. In that case, it's better to go to a technical plastic like ABS that can resist, for example, 100 degrees. There are all types of plastics. And you say metal, wood, yes? Depends on the plastic. Most of the plastics are like thermally insulated, but you have some plastics for 3D printing that they are conductive or semi-conductive. That, for example, there is a plastic that is called graphene filament. Let me finish this. It's just after this. You say metal, wood, TPU. You say, can we print with metal, but are we not melting plastic? Yes, actually, all these filaments are plastic-based with additives of metal, additives of wood, additives of, for example, conductive things. For example, graphene filament is, in general, is PLA with graphene particles, and the range of percentage of material extra of additive of that plastic will vary. For example, last week I was printing with carbon fiber filament. Carbon fiber filament is carbon fiber, carbon particles at 20% mixed with PETG. So actually you never print the full metal. Copper filament is just copper dust mixed with plastic. So actually you get a little bit the aesthetics and the touch and the appearance of that metal, but it's never completely fully metal because we don't melt copper at 200 degrees.
All right.
Thank you. Like, really good point. They say MDF is not wood. Yes, exactly. This is not wood. That's one of the next thing is like, for example, wood filament is not wood filament. It's wood dust mixed with plastic. And they have also bamboo dust milled with plastic, lignite, different types of lignite milled with wood. Actually, for example, one of the best filaments I have tried so far is hemp-based, like cannabis-based filament. Prints really, really well. It's strong and it's really light and it's beautiful and smells good also. Like doesn't smell like cannabis. It smells just good. You have TPU. For example, there are like thermoplastics that are flexible ones. This list of materials is endless. Like we can easily count right now more than 200 types of plastics that you can produce with FDM plastic. But these are the most standard ones. We consider PLA, like 90% of people print with PLA. It's easy, strong, reliable, easy to produce, it's fast and cheap, has everything. Like for me, is the winner. Then we have PETG. Is something between ABS and PLA. It's stronger. It also is really, really flexible compared to ABS or PLA. So if you want to produce pieces that flex a little bit, recommend to use PETG. On the other hand, the surface quality of PETG in general is worse than PLA. It's easy to print and is food safe. Food safe, there is a lot of papers if something FDM printed is food safe or not. If you want to make it fully food safe, you will need to change a few parts, like let's say baby proof. You need to print plastic that has been properly cleaned up, then sterilized. The machine needs to be sterilized, and then you need to print with a plastic that doesn't have any colorants, because colorants are also something that embeds pigments that usually are not especially food safe. Yes, some questions around there?
Kugla sastavljena od lamela. Nešto,
I don't hear you. You don't speak louder.
Što bi rekli, kad bi vidjela, znala bi.
PETG.
Onako kao zemlja,
It's a petroleum-based plastic. If you want the name,
sastavljena je od lamela, jer ne možeš Ne mogu oblu površinu izvući na print,
It's a
na
copolymer.
laseru. Kužiš per ploče. Ali mogu napraviti lamele.
This is PET. This is the water
I na
bottles.
lamele mogu ucrtat kartu. Kužiš tako da bočno su kao karta. Kužiš, ne napred, nego bočno ti je karta.
Glycol is an additive that we add to actually enhance the printability. Basically, it makes the print material smoother and easier to print, even if it reduces a little bit the strength. The deal that we got versus printability versus loss of strength is good enough that we always print with PETG and not with PET, because PET is a material that doesn't tend to print that well. So we have nylon, a standard, really high technical plastic, really nice, really annoying to print on the other hand, but you get really strong and performative parts. Why? Nylon is hydroscopic material. That means grabs all the humidity of the air. And when you let plastic grabbing humidity and water content of the air, what happens when you heat up water? It boils, no? And produces steam. Imagine this in a really small scale. The plastic that you are melting, if it has water content and has too much water content because it's hygroscopic, will actually create steam inside the plastic and will produce small bubbles inside the plastic, reducing your print quality. So actually nylon is a material that you need to save in a complete sealed bag with silica, and you want to actually cook it a little bit to reduce the amount of water, the content that you have, in order to print it. Not only considering that the print temperatures that you need to use is way higher. Usually nylon prints up to 70 degrees, that not all the printers can afford to print at those temperatures. TPU, flexible filament, what we commonly know as flexible filament, and we have PE and PEC materials that are like one of the strongest engineering plastics that we can print, but this one, for example, prints at 450 degrees. Right now, we don't have any printer that here that can reach 450 degrees without melting itself. In slicing, most of the CAM softwares, when we slice, you have like the 3D standard point of view. That is, for example, you see the 3D models. You can always choose also to see the overhangs. They will tell you where your model is prone to fail or where it will fail eventually. So it will warn you, showing you with a visualization, for example, where the model will fail and where you will need supports. Transparent visualization, X-ray, in case you have complex models that have some hollows and cavities. This mode is always useful to see the overhang angles that you need inside your parts. And then you have the layer view. As far as it's a good slicer, it will show you the layers and actually the real three-dimensional lines of your print path in the digital world. That means you are able to see how your model will actually look like layer by layer on the 3D model. Let's go a little bit over a few samples of 3D printing parts, and then let's go on the slicer. I will try to be a little bit brief, because today we started a little bit late because someone was late. So for example, what happens when you want to produce large objects? One of the biggest constraints of 3D printing in general is you cannot print a large object larger than your 3D printer. And usually the 3D printer size is small. Like the average 3D printer size, like in a household environment, is 200 by 200 by 200 millimeters. That's the average one. Of course, you can find 3D printer that they print more or less 400, 400, 400. We consider household big scale printers. So far, industrial 3D printers, the biggest one that they sell is called the Big Rec. And it's 1.2 by 1.2 by 1.2 meters. It's huge, it's bulky, it's fancy, and this more or less costs like 30,000 euros. But can print, let's say, a full bike frame or a wheel, etc. And this is one of the industrial's FDM printers. In general, a 3D printer is weird to find a printer that produces, in any technique, larger scale than 400 by 400 by 400. So when you design something, you always need to be thinking out how you can modulate your design in order to produce a small part or compounds that becomes and translates to your geometry. So in this case, for example, here you could find the references. You have these small parts that actually they match like a giant three-dimensional puzzle to actually produce this kind of shelter. Concrete slab, for example, 3D printing is widely used also. Here, for example, this slab is architecture slabs for making the roofs or the ceilings. In this case, 3D printing was not meant to be used as the final output. It was meant to be used as the mold for the slab. So actually, you 3D print a really complex mold, and then you, for example, you can cast concrete to produce an optimized, generative optimized, and reinforced slab that actually improves the performance of the slab. I just said that it's difficult to find big 3D printers. That's the only 3D printer that actually exists in the world right now. Is the D-shape of Gianluca. Right now is in Italy. I don't know the city exactly. This basically is a building like this, that the whole building is a 3D printer. So the same as you have here, like the beam, because it was a old factory, they have a whole beam, that is this one, that injects a binder to harden this concrete. It's not exactly concrete, it's their magic formula, it's his patent, and to produce like objects. So in this case, when they want to take, for example, this shape out, they need to take actually like a good pair or like strong woman and men, start digging out all the power out, and then take with some scaffolds and some heavy equipment the pieces out, because this is concrete, but this is to print large scale. Big printing also, when it comes to big size printer, and in FDM in this case, you have, for example, shop architects that they use the facilities of Branch Technology in Tennessee, I think it is, that they use pellet extruders attached to robotic arms. So actually the print size is not constrained by the machine, but is constrained by the reach of the robotic arm. Here is something that, well, you have seen this last Monday that we went through with robots. What is the volume that the robot can print? Actually where the robot can reach. Or here, well, you have seen here like the OTF guys printing clay, kilos and kilos and kilos of clay, in this case, with a pneumatic syringe, and this year also with a extruder that was designed by WASP. The same as you tested with the paste extrusion in one of the maker clubs. This case, for example, is also a full building size printer. You see the size of this is quite weird to find. Or just a few fancy examples. Printing preparation. As someone pointed out last week, we always work in millimeters. All the slicer program work in millimeters. So always when you design in millimeters. Always think into account what is the print size of your machine, or the machine that you want to use. If your machine size limit is 200 by 200 by 200, don't go and produce a model of 200 by 200 by 200. Probably your model will need to be reduced to 195, 195, 195, because you need to leave a little bit of offsets on the sides to allow to print their object. Always recommend to save the object in STL and OBJ in closed shape. It means your object needs to be a watertight geometry. You cannot print just a wall. If you want to print this doesn't exist in the real world. Please, can you show me a surface? No. A folio paper, that is the close approximation to a surface, has a steel thickness. Really thin thickness, but has thickness. So when you want to design an object, your object needs to be a three-dimensional shape. Cannot be just a surface. So it needs to be a geometry that has volume, not just 2 dimensions. It also, your geometry needs to be watertight. That means you need to imagine your 3D model as if you fill it with water, can the water escape from it? It has a hole where the water can get out. If the water can get out because it's missing a surface, you cannot print it. Even so, most of the standard like slicing programs, we actually try to solve and fix these kind of issues in your model, but they are not bulletproof. Always think about the overhangs and slope angles. Okay, modeling softwares, time is a factor. We'll go directly onto the hands-on. So there are a lot of types of slicing programs. One that we use in the house is Cura. Depends, for example, in the other building, in P59, they use some machines that are short tracks can only use their proprietary software. Here, for example, we try to choose printers that you can use multiple slicers with them. Cura is a software that could be even used for kids or for adults because it has high customization. We can choose to see all the parameters that we want or just a few of them. Don't get afraid because I will have a lot of parameters, but in general, what you will choose is, do you want infill, supports, layer adhesion, and what is the quality that you want to print with? Cura works by showing you the size of your 3D printer. And one of the most important parts that actually Adai and Mikkel will explain you later is we have 6 types of different 3D printers. Each machine has a little difference. Some of them are bigger, some of them can print higher temperatures, and by so you need to customize the file for each one of them. So the first thing that you need to do is choose the printer you want to use. If you don't choose the appropriate machine that you want to use, bad things will happen. In general, you will break a little bit the machine. Best case scenario, the machine will only get miscalibrated because some machines, the machines in general, are really silly. If the file is telling the machine to go 300 millimeters on the right, the machine will go 300 millimeters on the right, even if the machine is only 200. The machine doesn't know its limits in general. So the machine will actually crash to the side trying to go further. So one way to avoid that is actually to choose the machine that you want to use. For example, this is my house printer that I was printing yesterday. I will choose to print in one of the printers that we have here, so we will click and go onto Cosel. As you see, the printer shape has changed a lot. And right now, for example, this printer is a Delta printer, has a cylindrical workspace. Then we can launch a few files. For example, I will put a complex 3D model, so we can see. I want to print this object. This is an object that could only be made subtractively. Has high complexity, has holes, has a quite stiff geometry. It's an object that also I need to print really strong because it's a structural part. So let's go over the settings. The first settings that we can choose is always the layer height. The layer height is determined by the quality. Smaller layer height takes more time. Bigger layer height takes less time. As simple as that. For example, a standard layer height for fast printing or draft printing is 0.3 millimeters. Let's slice it. Let's see. The slice it is produce a file for it. We are slicing it, and it's saying 5 hours, 11 minutes. Let's see if we print at 0.1.
Hey.
Doo-doo-doo. 15 hours. 3 times more time. The material expand is exactly the same. But what is happening? Let's go to the layer view. If we go to preview, it will take time to load a little bit. Let's hide protein panel. Here we can see in different colors the movements that the machine will do. For example, we have the purple ones are movements in the air. And here we can see the layer heights. You see, let's go closer. The layer heights here are really, really small. Let's try to visualize the 03. Right now, you see the layers are way bigger, and also informs the design. We have more things. For example, we have the shell. It means what is the thickness of the outside wall. Right now, I have 3. This is not 3 millimeters. It's 3 walls. What is the thickness of a wall? If the nozzle of the machines, this is the point of the machine, this guy has a little space. The nozzle is 0.4. So that means as one wall, a single line or path of the machine will do 0.4 millimeters. If I want 3 walls, it means the machine will pass 3 times, 2 walls, 3 walls. That means my wall thickness is 1.2 millimeters. And it's important to understand this because, for example, the big machine that we have, the nozzle, blue, the nozzle of the big machine is 1 millimeter. With just one wall, we can achieve the same thickness almost. With 2 walls, we get 2 millimeters. So it depends on the machine you use, you need to set up some walls or less walls. In general, most of the machines, they are 0.4 millimeters. We have only 3 of them that are special, so we have custom nozzle sizes. Then we have top layers, 3 and 3. And this number is not set up. Why? Because it depends on the layer height. If your layer height is 0.3 and you have 3 top, it means we have 0.9 in total. If your layer height is 0.1 and you have multiplied by 3, it means the total is 0.3. So these numbers, what is shell, clear all drawing, top and bottom layers needs to be adapted, depends on the layer height that you use. Let's go to see a little bit the wall. We have a sliced. Here, we can see the 3D model. And we have this slider. This slider allows us to cut the model a certain height. So you can see here that, for example, we have 3 walls, 1, 2, 3. They have different colors because the red one, it means the one that touches the exterior, but it's the same setting. Let's set up, for example, 10. 10 is for making a super strong structural part. Right now, I just fill everything because basically it takes the outer shell and start making offsets until the interior. In this case, what we did is just fill the interior completely. Let's set up only 1. And we have only 1 line of the exterior. To see the top and bottom layers is slightly more difficult. For example, we need to go to the first. Second, it's difficult to slide only 2. 2 and 3. You see that it's changing the pattern because it's overlapping different directions for the first, second, and third layer. If we just set up 1, it will just make 1 full surface. Let's go over another one. That is the infill. Right now, this model, for example, here, we have an infill of 30%. 30% an infill of lines.
Tako je. Ta oni rade.
You see, we only have 1 lines in one direction, and the previous layer was lines in the other direction. It's overlapping at 90 degrees, the lines. Let's change, for example, for lines at grid. Grid will create
Riba.
a grid
Yeah.
of infill.
Ko je jak?
And the spacing changes because what keeps
Ide.
is always a 30%
Ajde da
material
vidimo
density.
kako će to
Another
ići.
commonly used, for example, is
Ajde.
a tri-hexagon. Different infills have different approaches for the geometries.
Ajde.
Oh, no, we are not recording. Sorry, no, we forgot. No, I thought it was recording, but no, it's not recording. Okay, we lost today class. So we have triangular one. It doesn't matter to like record now. It's only like 5 minutes left.
I'm recording if you need the video.
Oh, thank you, Tatiana.
No problem.
Will you send it later?
Yes, I can.
Okay. We have gyrode. Gyrode is a kind of good infill. Let's slice it. That basically is creating a minimal surface that is slowly changing side to side. It's transforming from one direction to another one gradually. But in general, most of the times I use triangular infill, like good all-around worker, for almost everything. For example, let's increase the
Kaži.
infill density to 70, even if it's a little bit
Kriva će ga
useless.
spasit.
Let's go and see.
Da. Ajde da ga
Inside.
spasi.
For example, right now we jump to have this density, and it's taking 5 and 10 minutes. Let's change to 10%. 3 hours and a half. We just reduce 1 hour and a half just by changing the infill. Of course, this depends on what is your piece and what you want your piece for. My recommendation is never go in grid below 10%. Why? Any clue? No? Okay, think in the total space that we have here. This is an empty space, no? Right now, we are trying to close this area. It means we need to print from here to here without support. Suddenly, we are going to make a full layer, this one, that is going to be printed in the air. So that means the material will probably fall in the first layer, the second layer will not fall that much, and the third layer will get actually a good surface finish. So in order to print in this area, you need to make a big jump in the air with the melted plastic that is going to create an overhang. So actually, the plastic will start like dropping a little bit and create like a spider net, like not clean spider net, and then we will print the next layer. I will fix a little bit that spider net, and then create another one. So in this case, when you reduce the infill a lot, you have problems of surface quality. It means the exterior quality usually gets reduced a lot in the top and the bottom. There's the top bottom not that much, but it's especially the top. So my recommendation is stay always on the 15% threshold, unless you really know how your geometry works. There is another way. For example, you can have a really small infill, but add a lot of layers on top and bottom. But that is the balance. For example, infill prints faster than top and bottom layers in general. For example, you will be able to see it here, speed. Top bottom layers, they print at 25 millimeters per second. Meanwhile, for example, infill prints at 50, it's double speed. So sometimes, actually printing less infill doesn't reduce the time, because you need to compensate with exterior walls. So it's a balance between both. And that's actually with the values that you need to test and set up for your each individual 3D printed models. Depends on what you want to print, you always need to customize all these values. That's why, for example, I have all these numbers open. Because if you start playing a little bit with the values, and you start touching, you can save like hours. Yesterday I started printing this file at home, and I just used last day settings, and it was calculating 7 hours. I set up the numbers accordingly, and it took 4.5 hours. Almost saved half the time just by setting up values, and still with the same quality.
Făcut ce ona pas dole onda.
What else? We have the material, and this is the print temperature. For example, in this case, it's using PLA. We only use 210 degrees. And that's weird. But here also there is another temperature that is called the bed temperature. I don't know why it's not showing up here. But this, in case of PLA, we will need to set up bed at 60 degrees. So for example, what happens if you set up a value that is really wrong on Cura? It's warn you with, for example, yellow. This is a weird value. Like, not everybody can print at 350 degrees because most of the printers cannot print at 350 degrees. They have mechanical constraints. So Cura, in case you made a big mistake, will warn you. If you print at 1000, it's weird. Sometimes they show the value in red. That means this is going to fail for sure. Yellow is probably fail. What else we have? The speed. Most of the 3D printers, they work at between 20 millimeters per second to 80 millimeters per second. And this is about the machine quality, settings, how you need set up. The standard printing speed is 50 or 60 millimeters per second. You don't have a lot of speeds that they will automatically update when you change the main speed driver. For example, if you print at 80, all the rest of the speeds are calculated automatically. But for example, some materials like ABS or nylon or flexible materials, especially flexible materials, need to be printed really slow. For example, flexible materials need to be printed at 20 millimeters per second. Why? Imagine printing with something that is flexible. It's going to be fluffy and it's going to move all the time. So you need to go really slow so the print doesn't move, meaning while you print. You need to reduce a lot the printing speeds. Average printing speed is 50 or 60. Trouble. We don't care about this too much. Cooling. The printer has some fans that cools the print while we print. In general, unless you use a really specific plastic, you always have the fans on. And supports. This is really important. If we don't have the automatic support generation, let's say no supports, my printer is exactly my model. What happened? This is a breach. It will fall, for sure, like 100% sure. So I cannot print cantilevers. I cannot start printing in the air. So we can choose to print two kinds of supports. Let's go over them. Let's generate supports, and you have options. Everywhere or only touching build plate. Let's see what's that. Let's go touching build plate. So right now, the blue are the supports. We have supports in the areas that are only touching the surface, but not supports in this area that is on the model. Why? Because supports in general, what they do is like they reduce the surface quality. That means if we have a support here, the support is basically the same material glued against your model. You need to cut this with some tweezers, pliers, etc. So sometimes happens that this also reduces, if you have support here, also on the bottom, also reduces the surface quality here. So in some cases, you only want support in the part that don't touch your model. In this case, this model will be really difficult to be printed without supports. So in this case, we want to have supports everywhere. So right now it's printing supports. What happened? Right now this support is attached here and here. So in some cases, this depends a lot on the 3D model. I cannot say like this is correct, this is not. Depends on your 3D model you want to print without supports, only touching build plate, or everywhere. Build plate adhesion. When we print, the most tricky part on a 3D print file, and I will say all the machines, we have the 3 minutes of danger. When we launch any file, 3D printer, laser cut, CNC, if nothing bad happened during the first 3 minutes, probably nothing bad will happen during the rest of the file. If you have messed up something, it will have show up in the first 3 minutes. In 3D printing, that is quite strict and mandatory. Why? Because we need to print on the top of the surface. So that means we need to attach a material on the print surface. And this, usually, we are working with really small tolerances. What is the tolerance we work with? Your layer height. Your layer height is 0.1, 0.3 millimeter. So the 0.1 millimeter difference can make that your model doesn't attach properly and your model moves away. So it doesn't stick to the platform. There are ways to solve this. It's by heating the platform, and one of the easiest ways is to actually print with a kind of foundation. We can set up to print with Brim. Brim will create an external layer of adhesion around the model. You see this new blue line? It's having like a more contact zone on the surface, so the model actually grabs properly on the build plate. And this is widely and usually extended. So it adds a really thin layer of 0.3 millimeters and makes like a fit all around your model. This fit is 0.3 millimeters at the worst case scenario. So in general, it's really easy to break it and it doesn't reduce your surface quality. If your model is really difficult to attach, for example, let's say, I don't know why, but in this case, I want to print my model like this. Let's say, I'm crazy today. The contact zone here is ridiculous. So that means the model will fall. It doesn't have any support. I will want to print with a graph. Graph creates a foundation around my object. So actually, it creates a foundation, let's see, preview. So creates some layers of pre-material that is going to be trashed after we print, and then start printing the model on top. So creates a big foundation of material to attach properly on the bed, and then places the model on top. My recommendation is never print with graph, because this is a lot of waste of material, not only waste, but is difficult to remove in general. This is for parts that are really difficult to print, that you cannot make it to attach to the bed properly. In general, if the bed is clean and the machine is well calibrated and you are using the proper temperatures, with green is enough. You don't need to do anything else. And then we have special modes and experimental modes. With this is how we have how we slice any 3D model. There are other softwares, for example, Slicer or Slicer 3D or StructTrax that actually produce files, but in general we try to use Cura because it has a good balance between easy on the program and customization possibilities. For example, you will see that the values that we have there are different and I have different options. Why? Because here you can customize. These are all the settings for machines. And you can customize what you want to see and what you don't want to see. For example, I don't want to show the parameters for support line width or skid line width. So in this case, I don't have this chosen. If I choose this, for example, wall extruder, it will show up here, the different settings, as long as I start clicking on them. So you can make this program really easy, or you can make it really difficult. Depends on your knowledge. Okay, it's already 12. So let's have a little break, 5 minutes, and let's go over the stations, okay? Do you have any questions just before we move? Yes? Sorry? In general, the supports, they don't touch perfectly on the surface. They stay like half the layer height against your model. So the touching contact zone, in theoretically, is really soft. So in general, you can just take some pliers and break them out, because the supports is just one line. The line is 0.4 millimeters. So I think 0.4 millimeters of plastic in general is really weak and easy to break. Depends on the plastic you use also. For example, PLA supports are easy, ABS supports are really easy, PETG supports are awful because the material bonding is really strong. There are some types of printers that can print two materials at the same time. So you can choose to print supports in one type of material and you're printing another type of material, because there are materials that they melt. For example, PVA is a type of plastic that melts if you put into lemonade. So actually you can print your model with supports, put in a bucket full of lemonade, and you melt out the supports. This is for B-material printers that in general, they work, but they have a lot of constraints in, like, they get stuck a lot in general, like they are not that straightforward to use, and they need constant calibration. They need a lot of maintenance, but they print really well. And I will show you one of the printers two printers have dual materials, so we can print two different materials at once, or the same material with different colors. That is also cool. Okay, let's have 5 minutes, but real 5 minutes, okay? Really short bio break. And I will ask you to please clean the tables, because at 1 they will come and clean all the tables because there's something later on, okay? Don't leave anything else. If you want to leave your bags, just put them inside the academy room. Thank you.